I believe this is on page 27 of your unit handout. So the first part of the lesson is just a lot of, first part of the lesson is just a bunch of theory. I don't mean to say just a bunch, like it's not important. It is important. We're going to be defining gravitational potential energy and defining kinetic energy. And this is elevated from what you would learn in Science 10, where you're just told, well, here's the formula for gravitational potential energy. Here's the formula for kinetic energy. Here we want to understand where they come from and what they mean in terms of work. And then we're going to be solving problems using the definition of gravitational potential energy and using the definition of kinetic energy. So to begin with, we need to remember throughout today's lesson that work is a transfer of energy. So when you do work, we know work is done because you apply a force to an object and the object moves either in the same direction of the force or in the opposite direction, or in the same or the opposite direction to some of the force. The force doesn't have to be exactly in the direction of motion. It can be angled a bit. But there must be a component of the force that's in the same direction as the motion. And we learned that that's how you can calculate the work, by taking that force in that direction times the displacement. What we're going to be looking at today, though, is going to be energy in general. And we're going to be able to apply a different definition of work to this energy, namely that work is a change in energy. We're going to start with that day after tomorrow. So in general, there are 4 different types of energy. And when you get to Physics 30, we change this definition slightly, and I'll talk a bit about that in here. One type of energy is kinetic energy. Kinetic energy is an object in motion, basically. If you have an object that has mass and it's moving, it has energy. What does it mean to say an object has energy? It means it has the ability to do work. What does it mean to say an object has the ability to do work? It has the ability to apply a force to something it comes into contact with and move it through a displacement. So a baseball has kinetic energy because if you've ever been knocked in the head by a moving baseball, you know it applies a force over a distance, right? It transfers energy to you. It does work. This is one of the most important aspects about kinetic energy. Kinetic energy is the result of a net force. I can apply a force to an object all day long, and unless there's a net force, I'm not going to give the object kinetic energy, because a net force results in acceleration, and acceleration is a change in speed. So just from a basic standpoint of acceleration, even a grade 9 science explanation, if something accelerates, it speeds up. There's more advanced explanation in Physics 20, but in order to get an object to be moving faster so it has more kinetic energy, it has to accelerate. So there has to be a net force. So the work done in this specific case is equal to the gain in the kinetic energy of the object. And there's a correction in your notes that I will get to in a second. But what I'm telling you is the work done is force times displacement, but if you use the net force, you get the change in kinetic energy. And this is going to be a useful thing to know. And I'm not changing the rules here. The rules are applied forces, work done to an object. But if I apply a certain force to an object, giving it a whole bunch of energy, some of that energy might be potential and some might be kinetic. There will only be kinetic if there's a net force. Something got scrambled here when I edited this document last time. It says, assuming the object does not gain other types of energy like potential, or I think it just says, or frictional. Frictional is not a type of energy. Friction is a force. So what that should say is, provided it does not gain other types of energy like potential energy or heat caused by frictional forces. Heat is a type of energy. It's caused by a frictional force. So we have kinetic energy, and again, I think this is, well, I know this is going to be important for later, that it's the net force times the displacement which gives you the change in the kinetic energy. And my computer's just jammed up here. I'm going to give it a second. Potential energy. So this is the type of energy that is stored in an object waiting to reveal itself. So a stick of dynamite, TNT, which is trinitrotoluene is what the chemical name is for it, has chemical potential energy. There's energy stored in a stick of dynamite that given the right conditions, you can release the energy and it can do work. You need to light a fuse and you need to add a little bit of energy to cause the chemical reaction to occur. If you take chemistry, you might have, well, I don't know, you guys are only in grade 11. Have you talked in chemistry about catalysts? So a catalyst is something that causes a chemical reaction to occur. And very often a catalyst involves adding a little bit of energy to the chemicals to get it over this hill where it can release all of its energy. And that's what lighting the fuse is. A Snickers bar also has chemical potential energy. When you eat the Snickers bar, you ingest a whole bunch of carbohydrates, basically, a bunch of sugar, and your body, through the process of cellular respiration, pulls energy out of that sugar. It also pulls water out of it, and it also pulls carbon dioxide out of it. A 2-ton safe suspended 10 feet above Wile E. Coyote has gravitational potential energy because if you cut the rope under the right conditions, that safe can do work to other objects. A coiled spring has elastic or spring potential energy. So we're going to be doing a lab tomorrow in which we look at springs stretching and compressing. And we often say it has spring potential energy or elastic potential energy. Elastic potential energy doesn't necessarily mean you're dealing with an elastic band. It means it's something that's springy. 2 grams of nuclear material like uranium-235 has nuclear potential energy. The electrons in a battery have electrical potential energy. I'm trying to point out that although when we talked about kinetic energy is kinetic energy. There's just one type of kinetic energy. There are many types of potential energy. There's electrical potential energy, there's magnetic potential energy, nuclear, chemical, gravitational, elastic. But there's only one type of kinetic. Is that clear? Okay. There's also thermal energy, and what thermal energy is heat. So an object that is hotter has more thermal energy in it. Now, this is a tricky thing because heat is a sensation that we detect with our body and our brain. So how do we quantify it physically? Like, what is it in terms of physics? Well, it's a type of kinetic energy. It's a very specific type of kinetic energy. When an object is hotter, all of the molecules within it, or atoms, if it's a piece of metal, say, and doesn't have molecules, all of the molecules are moving faster. But they're not all moving faster in the same direction. I mean, if I take this stapler, would you agree the stapler has some kind of temperature associated with it? If I throw the stapler across the room, and I'm not going to do that, while it's in the air, would you agree all of the molecules are moving faster? But they're all moving in the same direction. And collectively, we'd just say the object has kinetic energy. If, however, I put this, I don't know, in a sink filled with hot water, the object itself is not going to gain kinetic energy, but all of the molecules making up the object are going to start moving faster. They're just moving in random directions. So what heat is random motion of molecules. And we sense that by touching things. When you touch something that's warm, that random molecular motion of all those molecules jostling around hit the molecules in your hand and on your skin, and those molecules move faster in random directions, and our brain senses that as heat. If I take a ball, a rubber ball, and I don't have one here, but if I take a rubber ball and I bounce it from here kind of at an angle, you know intuitively it's not going to rise as high every time. Which means that the ball is losing energy. And eventually the ball will peter out and it will stop. And the question is, where did all of its energy go? And that's an interesting question because at different points in the ball's bounciness, it's got some kinetic and it has some gravitational potential. But in the end, the ball's just sitting there. Where did all that energy go? Well, it turns out every time the ball hits the floor, it doesn't rise to the same height, does it? So every time the ball hits the floor, it loses some energy. And it's hard to imagine, but that spot on the floor where the ball hit is warmer because of the collision. And all of the molecules on that part of the ball that touched the floor, they're moving faster as well. So what's happening at the end of it all is you've got all these little patches of heat on the floor and the ball is hotter. It has a higher temperature. And finally, light energy. And it's really a hard thing to quantify because, well, until you get to physics 30, we're not talking about the energy an object has, we're talking about light. Light is simply a pure form of energy. It's a special situation. It's best described as energy in its purest form. And you can convert light to other forms of energy. You can convert light to heat. If you've ever sat on a beach in the summer, you know that. You can convert light to electrical potential energy. If you've ever had a solar calculator, that's what's happening. And you can use that electrical potential energy to run a motor, creating kinetic energy. So it's possible to take light energy and change it into something useful. We're going to start off by looking at gravitational potential energy, and we're not going to use a formula. Whatever formula you think you know, just forget about it for a second. We've got some kind of a ride where people are in a car and they're raised to the top of this thing, or they're raised up to a height, and then it's released and you're in free fall. If the car and the passengers in the ride have a mass of 500 kilograms, what's their change in gravitational potential energy as they are lifted through a height of 48 meters? So, we are not using a formula for gravitational potential energy. We're going to use the definition of work. The work done is going to be equal to the gravitational potential energy. Well, the change in gravitational potential energy. So, if you're talking about gravitational potential energy and you want to find work done, this is force times displacement. Are you with me? Okay. But what's the force? Well, it's the applied force. But if you're talking about working against gravity, then that force is the gravitational force. And what we have to assume here is that they are moving with zero acceleration. Whoops. They are moving with zero acceleration. They're not accelerating. Do they have kinetic energy? Yes. But is there kinetic energy as the ride is lifting them? Is there kinetic energy going up? No. So this is the applied force times the displacement. Well, the displacement is going to be 48 meters. Who can tell me how we can find the applied force? Ryan.
Is it MGH? Is it MGH?
I'm just asking just about the force right now. You're one step ahead of me.
Well, the force, applied force is going to be same magnitude but opposite to the gravitational force, so
Right.
mg.
mg. The applied force is going to be the same but opposite to the gravitational force, which means it's mg. And again, we are assuming something that all of the work is going into gravitational potential energy and none of it is going into kinetic. We've already talked about the fact that if some of it goes into kinetic, there's an acceleration. So there can't be an acceleration, which means the forces must be balanced. There's a lot going on here. We could just jump to the formula, okay? But there is a lot going on. Why are we assuming it's acceleration equals zero? Because we're asked for the change in gravitational potential energy. There's no kinetic energy change. So this is going to be m times g times d. Well, we can calculate that. That's pretty easy. We've got 500 kilograms times 9.81. I'm going to go with the newtons per kilogram here this time, times the 48 meters. It was 48, wasn't it? Yeah. So I'm getting 235,440 joules. Just confirm you're able to get that answer. Okay, well, what that is the change in the gravitational potential energy. Now, because there's just a little clerical item here, because there's many different types of potential energy, I will very often write a subscript with the subscript of P. But if I don't, I'm talking about gravitational. Okay? So that is the change in potential energy as they go to a height of 48 meters. It is not necessarily the potential energy they have. It's the change in the potential energy. And we'll talk a little bit more about that in a second. That's the answer to the question. Any questions with that example? Use the results to develop a general formula for an object's change in gravitational potential energy. Well, the change in the potential energy is the work done against gravity, which means it's the force times the displacement, but this is really the force of gravity. And I want to be careful here. It's the applied force upward which is equal in magnitude to the force of gravity. And this is where Ryan was coming from when he said mgh. But we're going to do this a little bit differently. We're going to put mg delta h because we are asked for the change in the gravitational potential energy. I know we've talked about this. I am racking my brain here trying to figure out where. We have talked about delta meaning change in a quantity. I'm using Q for quantity. And it's always final minus initial. Always. So I want to make a point here that if the initial height is 0, then delta H is simply the final height. And that means that we come up with this formula for the potential energy at a certain height above 0. And this gets a little bit tricky because with potential energy, well, let's have this conversation right now. Does this container of chewing gum have gravitational potential energy? Sure, because if I were to release it from this height, it could do work to the floor or my foot. Does the container of chewing gum have gravitational potential energy now? Well, most of you will say no, but what if I told you there was a basement in this building? And there is a basement in the building. There's a pool table down there, big screen TV. No. There's a furnace and all of the boilers and heaters and things like that. But there is a basement. So it is possible to talk about this container of chewing gum having gravitational potential energy here relative to the basement. And that's the interesting thing about potential energy for gravitational is you can choose H equals 0 wherever you want, and that will be important for later. Anyway, this is how we get this formula, and I suspect that in Science 10 you weren't explained how that formula arises. You're just told EP is mgh, but it has to do with you're working against the force of gravity and you're multiplying by a displacement vertically. All right, if you go to your formula sheet, you'll find this under momentum and energy. It's right here. It doesn't say gravitational, but you need to know that that formula is for gravitational. So a toy car is set up on a tabletop. What is the gravitational potential energy of the car, which has a mass of 0.025 kilograms relative to the floor? So when we do this question, we're going to say EP equals mgh. We're going to put in the mass, 0.025 kilograms, times 9.81 newtons per kilogram times 2.15 meters. Because what we are doing is we're essentially saying, when you say relative to the floor, we're calling the floor a height of 0. So let's calculate that. It's a pretty simple question. And I'm getting 0.53 joules. Okay. What does that mean? What it means is if there was a big ugly spider here, little hairy little thing, that car, if it were released and it went off the ramp and off the table and did this, it could do 0.53 joules of work to the spider, or whatever the object is. Okay? B, what is the change in gravitational potential energy of the car when it arrives at the bottom of the hill? I just want to point out to you that I could have said, what is EP relative to the tabletop? I don't have to say what is the change in gravitational potential energy. If I take a change in gravitational potential energy approach, then I use mg delta H. And this is going to be the mass, and look at that again, 0.025 kilograms, multiplied by g, which we all know the value of, multiplied by, and I know that some of you are going to think what I'm about to write is overkill. But bear with me. I can put here 0.95 minus 2.15 because it's final height minus initial height. The final height above the floor will be 0.95. The initial height is 2.15. So I can put in here 0.95 minus 2.15. Let's work out what this is. And again, I'm sticking to the strict rule that delta means final minus initial. Okay, that's what I'm doing. And what I get is a negative answer. And that makes sense. It does make sense because the car has less gravitational potential energy at the end than it did to begin with. If my bank balance was $10,000, I wish, and then later it's $2,000, my delta money is not 8,000, it's negative 8,000. I've lost it. And this object has lost that amount of potential energy. So the answer is negative 0.29 joules. On the other hand, if you took this approach and you just said, well, I'm going to find the potential energy it has at the top relative to the tabletop, well, what is the height? What is the height of the car relative to the tabletop? Well, it's going to be 2.15 minus 0.95, isn't it? Which is 1.25, I think. So this would be the mass times g times, has somebody had time to double check that it's 1.25 meters? 1.2, thank you. And what you're going to get is the same answer we got here, but it won't be negative. And that's okay. You're going to get the same answer. But what we do is we say that if the energy at the top is 0.29 joules, if we need to think of it as a change in energy, we would say it lost 0.29 joules. And that's what negative 0.29 joules means. Most likely, we're going to be working with what's to the left of this line, and then simply saying it's a loss. Quick question for you. If this car rolls down the hill and it loses 0.29 joules of gravitational potential energy, where did it go? You know, if I lose money, if I go out on a Saturday night and I lose money, it went somewhere. I have less money afterwards, it had to have gone somewhere. What if I told you it was frictionless? And it's probably pretty close to frictionless because the wheels rotate and don't rub as it's going down. And I've taken the car and I've given it a couple of sprays of WD-40 to really grease things up. So it's not heat. Kaylin?
Doesn't it become kinetic energy?
It becomes kinetic energy. So we could find the speed at the bottom if we wanted to. But I'm getting ahead of myself. Any questions with B? All right, find the potential energy of a 150 kilogram piano being held 12 meters above the street. That's a piece of cake. It's MGH. We are assuming that the street is the 0 point for the gravitational potential energy and for the height. You're not going to say, how do I know this question isn't asking me about the gravitational potential energy relative to the basement of a building 2 blocks away? Because it doesn't mention that. Okay, don't overcomplicate things. This is just MGH. So 500 kilograms, that's a pretty heavy piano. Multiplied by 9.81, multiplied by 12. Oh, 150. Thank you. That's more my speed for a piano. So 150 times 9.81 times 12 gives me 17,658 joules. Bless you. I think we're okay with that. 5, when work done is to lift when work is done to lift an object vertically at a constant speed, that energy goes into gravitational potential energy. When work is done to stretch or compress a spring or any other elastic material, the energy is called elastic potential energy. So if I take this and I do this, there's elastic potential energy in it. And I'm not going to let go, but if I were to let go over here, it's going to do work to my hand over here. Okay? So that's elastic potential energy. Kinetic energy is the result of work done to an object in order to accelerate it. And I want to demonstrate to you where this formula for EK comes from. You already know this. Correct? Okay. But I've told you earlier that the work done in terms of kinetic energy is force times displacement, but it's the net force that produces the change in kinetic energy. And that means MA. You do not have to know how to do this, but more and more I'm finding students who take Physics 20 and Physics 30 as well, being in a position where they want to know why things are the way they are. And I'm going to show you where this formula for kinetic energy comes from. Acceleration is Vf minus Vi over t. So I'm going to substitute into MAD this. By the way, MAD is always the change in kinetic energy. And that's a useful thing if you can remember it. And I was taught to remember it because when you get mad, you might throw things. So MAD, you're mad, you throw things and you give them kinetic energy. All right, I'm also going to use another substitution because displacement is VF plus VI all over 2 times T. So I'm going to have mass times the acceleration times the displacement the T's cancel, and I'm going to move this 2 under the M over here. And admittedly, if you're in Math 20 right now, this is easier to follow. But I've got M over 2, and then I have VF minus VI times VF plus VI. For you math people, what are these two things called? We just finished this, yeah.
Would be factors of the difference of squares.
They are. What do you remember what we call each of the factors relative to each other? They're conjugates. And when you multiply two conjugates, you get a difference of squares. If you were to FOIL this out, everybody, you would get the following. You would get M over 2, and then you would have VF squared. Your outer would be VF times VI. Your inner would be negative VF times VI. And your outer, or your last, would be negative VI squared. And when you do this, those two go away. They're opposites. And what we're left with is M over 2 times VF squared minus VI squared. But I'm going to multiply this M over 2 through. And I'm going to write it as 1/2 M times VF squared minus 1/2 M times VI squared. But what I've told you, if we go back to the top and see what this is the change in the kinetic energy. Which is final kinetic energy minus initial kinetic energy. That must mean that you can calculate kinetic energy using 1/2 mv squared. This is certainly not something you would have done in Science 10, right? You would never have been explained why that formula exists, but that's why. There's a reason for it. It has to do with, by definition, kinetic energy has to do with accelerated motion, so you use a net force in your work calculation. Anyway, here's the formula. It's a Science 10 formula, maybe even a junior high formula, depending on your science teacher. EK is the kinetic energy, M is the mass, V is the speed. Everything is in standard units, and on your formula sheet, you will find it above your gravitational potential energy formula. Good? Okay, let's try a couple of examples. Determine the kinetic energy of a 5-gram bullet traveling at 740 meters per second. So we're going to do 1/2 mv squared. It'll be 1/2. We need to convert that 5 grams to kilograms. The most common mistake with kinetic energy calculations, and this is just the beginning, this is not an exam question. It's not. It's a Science 10 question. We're going to be doing more with this, but the most common mistake is forgetting about that squared. And you might think, oh, I would never forget about it, but you might be surprised as well. I always enter the half as 0.5. And I get 1,369 joules. No problems there, I don't think. Okay. A 1,500 kilogram van has a kinetic energy of 300 kilojoules. What's the speed of the magical vehicle, which all of a sudden changed from a van to a car? What's the speed of the vehicle? Well, you're going to take this formula EK equals 1/2 mv squared put in the 300,000 joules, put in the mass, and find V. And I would want you to follow along very carefully with how I want you to do this. I have no doubt everybody can find the answer, but this is a calculation. If you were to ask my Physics 30 students how many times they've been in this situation and they have to find the speed from the kinetic energy, they would tell you over 100 easy. And that's because I mention it often. I say, you're going to do this calculation with the same or different numbers dozens and dozens and dozens of times. It needs to be just like that. You take the energy, you multiply by 2 to get rid of the half, you divide by the 1500 to get rid of the 1500, hit equals, now you take the square root. I want you doing it that way, okay? I don't want you wasting time by going 1/2 times 1500 and saying that's 750. I don't want you thinking of this as 0.5. I want you taking the energy, doubling it, dividing by the mass, and taking the square root. We're going to get 20. I can see that the square root of 400 is 20. So it's 20 meters per second. Any questions with number 2? All right. By what factor does the kinetic energy of an object change if the speed of the object is tripled? Would everybody agree that if an object is moving faster, it has more kinetic energy? Okay. Before we do this question, I want to throw this idea at you. If I lift an object vertically to a certain height, then at this point it has potential energy. Would you agree? What if I took that same object and I lifted it to 3 times the height? What would its new potential energy be relative to the original potential energy? Would it be more? Would it be twice as great? Would it be 100 times as great? How many times as great would it be? It's not really a trick question. 3, right? So if this is the initial potential energy, this would be 3 times that. Right? I'm pointing out to you using some language here, and symbolic language, that if you triple the height, you're going to triple the energy. Is that going to be the same kind of thing here? That if I have a speed initially, and then afterwards I have 3 times that speed, and maybe I shouldn't use initially. If I have before, and then a different situation which I'm going to call after, or situation A and situation B, it's not an initial final really kind of thing. There will be kinetic energy here. Will there be more kinetic energy in the second situation with the object moving faster? Yes. Again, that's not a trick question. It's not going to be 3 times as great, though. Does anybody know how many times as great it's going to be?
It'll be 9.
It will be 9 times as great. Because kinetic energy is 1/2 m of v squared, which is v times v. So if I triple v, I'm going to get an extra factor of 3 that occurs twice. And when I say an extra factor that occurs twice, I don't mean 3 plus 3. I don't mean 6. I mean 3 times 3, which is 9. So what you're going to have afterwards is 9 times the kinetic energy. You certainly could, if you're stuck on an exam, do the following. Let's take a 4-kilogram object moving at 2 meters per second and calculate its kinetic energy. Do it, 1/2 mv squared. I'm thinking you're going to get 8. Okay, take the same object, triple the speed, and calculate the kinetic energy. you're going to go 1/2 times 4 times 3 squared. I think you're going to get 72, aren't you? Oh, well, that's 9 times greater than 8. So you don't have to do it in an abstract way by looking at the formula. What you could do is just concretely pick numbers. How high does a 5-gram bullet rise if it's fired at 740 meters per second? Wait a minute. 5 grams, 740. Didn't we do this? Didn't we do something with this? What was the kinetic energy of the bullet? 1369 joules. So we have this bullet that starts at some point, and it has 1,369 joules of kinetic energy. Come on. And then it goes up to some point up here. We're trying to find out the height of that, but the kinetic energy up here will be 0. That's a fact. However high it goes, when it gets to the top, it will not be moving at that instant in time. You have a different question? What does your question say?
It's a 200-gram ball that's thrown up at 18 meters per second. We have to find
Let's do this one. Okay? Because we already have the energy. Maybe instead of crossing out anything in your notes, we'll do that one in a second. Okay? So forget about your notes and everything just for a second. If it were this, does this make sense so far? That at the top it's going to have no kinetic energy. Where will its kinetic energy have gone? Noah? Gravitational potential energy. And at the bottom, there's 0 joules of gravitational potential energy. So at the top, the gravitational potential energy would be equal to 1,369 joules. But now, what's the assumption? What are we assuming here? And with the bullet, it's a bad assumption. That all of the energy that was kinetic was converted into potential. Can somebody tell me where a lot of the energy would have gone, though, instead of gravitational potential? Heat, because there's a lot of friction because the bullet is moving through the air so fast. Okay. But if this were the case, we would just set this equal to mgh. Which would mean we would have 1,369 joules. Keep one to do that. Equals 0.005 times 9.81 times the height. So you're going to have to divide 1369 by the 0.005 and divide it as well by the 9.81. And you should know me by now. I would just do this in 2 steps. If you want, you can put the product of those numbers in brackets. Look at that. 2.8 times 10 to the 4 meters. Not likely. That's 28 kilometers. There's way too much friction between a bullet and the air. So what I'm going to do now is show you a more realistic example. But Ryan, can you tell me the mass of the ball and the speed? 200 grams at 18. So this is just leading up to what we're going to be doing in a few days. When it gets to the top, it will still have a mass of 200 grams, but it will be moving at 0 meters per second. And if energy is conserved from kinetic to potential, then the kinetic it has at the bottom would be equal to the potential it has at the top. That's interesting. So we can put in now 1/2 0.5 times v squared, which is 18, equals 9.81 times h. So 0.5 times 18 squared. What's that? Seems reasonable, doesn't it? I'm not sure, based on your comment, did you not get that?
What? Like the answer?
Yeah.
No, I got that.
Okay.
I had no idea how I was going to do this question.
No, and that's good. I like that because there's another woe coming up here. So you get 16.51376147 meters. Okay, no problem. But could we have done this? Could we have approached it from a kinematic standpoint? Yes, and you would have written Vf squared equals Vi squared plus 2AD. Vf is 0, so this would have become the following. Which would mean if we move this Vi squared, I'm going to move the 2AD over. 2AD, okay, negative 2AD equals Vi squared. I regret putting the negative for 9.81. My explanation would have been a little cleaner without it. But what I end up with is V squared equals 2AD, but that's what I have up here. I have V squared equals 2 times G times H. It's the same formula. There's an extra negative here because I chose to put the 9.81 as negative. Right? So the kinematics formula is V at the bottom squared equals 2AD. And here it's V at the bottom squared equals negative 2AD, but I put the negative in there for A. I really regret doing that. It's the same formula. And what you're going to discover, hopefully within the next few days, is that solving problems with energy ideas is a lot simpler than solving them with kinematics. A lot simpler. Okay. So there are two sets of problems here. Assignment A deals, I think, with gravitational potential energy. Assignment B deals with kinetic. I apologize, I feel as though I'm a little off my game this morning. I don't know why. I haven't